Hi, my name is Rahul Shah. I'm from Louisiana State University, and I'm going to talk about LF Successor, which is a method to derive compact index for a particular pattern matching problem called order-isomorphic pattern matching. Uh, this is joint work with my current and past students. So when we talk about pattern matching, what is pattern matching? So we have a text T and we have a pattern P, and we have to find where all does this pattern P occur in the text T. So there are a lot of algorithms which are known, which are very optimal in terms of size of pattern and size of text. However, when we talk about data structures, uh, we have that text T is already known in advance, and we can pre-process it and make some data structure out of it. And then pattern P comes as a query time, and we have to efficiently find out very quickly whether pattern P appears in T or not, and where does it appear. So for this, there are well-known data structures called suffix trees and suffix arrays, very powerful. They take linear space. They answer the queries in very, very optimal time. However, in those days when this was well researched, by linear space, it was meant when we count it in bits, it becomes big O of n log n bits. However, the text size is big O of n log sigma, and that's a complexity gap. And this gap also manifests when you look at DNA text, and then you see that suffix tree for human genome comes out to be 50 times bigger than the human genome itself. So that log n versus log sigma gap can be big. Now, many techniques were evolved in this field, like FM index, compressed suffix arrays, and compressed suffix trees. And many of these actually were reliant on Barrow-Wheeler transform and what is known as LF mapping. Okay, so what is the main template here to get an index of in n log sigma space, but not n log n bits, but n log sigma bits of space? Firstly, we compute a Barrow-Wheeler transform of the text. I'm not going to go into what that is, but you can say that Barrow-Wheeler transform of the text is a permutation of a text. So it just takes n log sigma space. It does not take more space. And then we use some data structures on top of it to compute what is known as LF operation. And we will focus quite a bit on LF operation in this talk. And I will explain to you what it is. So what happens is that once we know this LF operation, we can use this in combination of sampled suffix array to get a compressed version of suffix array. Okay, so LF is very crucial because you can use, if you can do LF, then you can do suffix array, then you can simulate a suffix array. In this paper, what happens is that for our particular problem, notion of Barrow-Wheeler transform is not that simple, and computing LF is again not that simple. So what we are going to do is instead we are going to compute what we define as LF successor. And then we, along with sampled LF array, we use LF successor to compute what the LF is. And then again with LF, we can compute with sampled suffix array, we can compute suffix array. And once we have suffix array, we can do pattern matching. So that's the main template. So what is LF mapping? Okay, so I'm going to reintroduce, redefine a little bit, reinterpret the LF mapping a little bit here. LF mapping was given based on Barrow-Wheeler transform, and it was basically mapping of last to front columns of Barrow-Wheeler transform. Not always we have Barrow-Wheeler transform, but think of this, we are going to think of this in terms of suffixes. So for example, LF mapping, what LF mapping does is that it maps a suffix into another suffix which starts at the previous location. So for example, take this text ABC, AB, AC, dollar. If you look at the suffix AB, AC, dollar, it starts at location 4, right? It left location 4. So this is AB, AC, dollar. This is a suffix here. Its LF mapping is just a slightly larger suffix by including the previous character in it. So that becomes CABAC, dollar. So this suffix is LF, is basically so since that starts at 4, now you go to location 3 and make suffix out of it. So LF of ABAC dollar is actually CABAC dollar. Okay. So basically it maps suffix to suffix, and basically it maps a suffix to its previous suffix in text. So that is what LF mapping is. However, what makes it non-trivial is that when we talk about suffix in this, we identify suffix not by this string, but its leaf rank in suffix tree. And we identify this suffix not by this string, but its leaf rank in suffix tree. So that's what it makes it non-trivial, interesting, and usable. All right. So now let's come to our. So this is very generic. This is just very generic in usual pattern matching. Let's move on to our particular problem that we are considering here, which is called order isomorphic pattern matching. So what is order isomorphic match? It's like if two strings have the same order, they represent the same order, kind of same permutation, then they are same. So let's say we have a string R1 through N and S1 through N. They're drawn from the same alphabet, and alphabet has order. Okay, they are order isomorphic match if take any ij. Okay, take any positions ij between 1 and n. If ri is less than ij, then si also must be less than sj. If ri is greater than rj, then si must also be greater than sj. If ri is equal to rj, then si is equal to rj. That means basically the ordinal relationship is exactly the same. Okay. So it means that their characters, when two strings are order isomorphic, their characters are in same rank order. Look at here, 2, 6, 4, 1 is isomorphic to 3, 8, 5, 2. Why? Because look at this, smallest occurs in the last position for both, biggest occurs in the second position for both, the second smallest occurs in the first position for both, and so on. So if you look at the ranks of each of these, they are basically in the same position. So that's why these two strings are order isomorphic. When we do order isomorphic pattern matching, right, we have this T and we say, okay, pattern P matches at T1 because 3 to 1 is same as 5 4 1. And it also matches at T5 because 3 to 1, that is also decreasing sequences, and 8 6 2 is also decreasing sequence. So it's the same permutation or same rank order. 3 1 2 matches at 4 1 3. So at location 3. Why? Because this is the largest, this is the smallest, and then in the middle. But it does not match at location 6, which is 6 to 9, because 9 is the largest now. Okay, so on. So that is what order isomorphism is. It has to basically say represent the same permutation. So this problem has been well worked on for last 8 years. There have been algorithms, and then there have been data structures. So there is data structure mainly, which is known as order isomorphic suffix tree, and there has been work on that. However, again, since this being suffix tree, just like usual suffix tree, it takes order of n log n bits. So now the question comes is that, is there a compact index? Is there a compressed index which takes order of n log sigma bits? This question was answered partially by Gaggi, Manzini, and Venturini. We got almost the compact index, but it only supports patterns which are of length less than polylog, and then it also has restriction that it can only output one match. So it's kind of a partial result, and what we give here is a full-fledged result for this, which actually gives big O of n log sigma bits index. Okay, so firstly, to show that two strings are order isomorphic, okay, we talk about a canonical representation, okay, or canonical encoding of these two patterns. So the position, so this encoding is called predecessor encoding, or sometimes you just call it as a pred encoding. What it means is that every position in the string basically points to another position to its left, which is just smaller in value than that value. Okay, so and then we encode this as a distance between these two positions. So and then we can show that two strings are order isomorphic if they have the same predecessor encoding. So in the previous example, for example, 2 6 4 1, right? We see that 2, anything to its left? No, so it does not have predecessor. 1, does it have anything smaller to its left? No, so they do not have predecessor. 6, does it have something smaller to its left? Yes, that's 2, so it does have a predecessor 2. And 4's predecessor is 2 also, right? Because some go to its left, something smaller than it, yes, 2. So 4's predecessor is also 2. So when we write it in positional form, we say, okay, n and n, because they don't have predecessors. 6 predecessor is 2, so go one step backward. So that is what its predecessor is. So for 6, you have to go one step backward to find its predecessor. For 4, you have to go 2 steps backward to find its predecessor, right? So it becomes n1 to n. Similarly, if you look at 3852, its encoding also comes out to be n1 to n. And since these are exactly the same, they match. So now, given this, we are ready to now make an index. So what is an order isomorphic suffix tree? What it does is that it takes all the suffixes of the text, okay? Now encode each suffix separately using pred encoding, and then combine these encoded suffixes into a trie. And that's basically it. When we do a pattern matching, what do? Again, we see the pattern, we convert the pattern into its pred encoding, and then match it in the suffix tree. just like a usual suffix tree. So let's look at the example here. Let's say our text T is 247195263, right? And these are all the suffixes of the text. Okay, I'm listing all the suffixes of text nicely. Now, if I take this suffix, these are for every suffix, these are the encoding. So this is the encoding. This is the pred encoding. So if I take this suffix 195263, that's the pred encoding. 1N 12322. Why? Because 1 does not have predecessors. Fine. 9's predecessor is one step back, which is 1. 5's predecessor is also one step back, so 2. 2's predecessor is also one step back, so 3. 6's predecessor, okay, 6 has many things which are smaller than it, 2, 5, 1, but the closest is 5, so it's 2 steps back, so this is 2. And 3's predecessor is 2, so it's again 2. So that's what these are, okay. These are basically, and these are the positions where in the text where these suffixes start. These are the positions in the text where these suffixes start. Okay. Two special symbols, dollar and N. N is the smallest, we can say, smallest of all the numbers, and dollar is the biggest of all the numbers. We are going to say. Okay. So these are all the encoded suffixes. Okay. Now we are going to put them in the suffix tree while we take care of these position numbers also for each of them. Okay. So firstly, what we are going to see is that when we talk about LF, right? So how things change. So let's say if I have this suffix here, 7195263, right? So I have this suffix here, 7195263, right? And it was encoded as NN22322 $, right? But when I moved it, when I took an LF mapping from here, okay? So when I do an LF mapping from here, I introduce 4. I move from this suffix 7192563 to this previous suffix. So I introduce this 4. As soon as I introduce this 4, 7, which did not have predecessor, actually found a predecessor now, right? So as soon as I introduced this 4, it did find a predecessor. And what happened here is that 5, right? So 5 here had a predecessor as 1, written as 1, but now it has a better predecessor, which is 4, which is a closer value, right? So what's happening here is that this first guy changed. This first guy changed, right? So this 5 basically. So this had earlier value as 5's predecessor was 1, so it was 2 steps behind, so it was 2. But now 5's predecessor is 4, so it is 4 steps behind. So all right. So when we moved from this third suffix in the text to second suffix, the suffix which starts in position number 2 in the text, right? Definitely, we added a previous character, and that always does not have a predecessor. It's always going to stay N. But amongst the other characters which are already in the suffix, we see that this N changed to 1, and this 2 changed to 4. Everything else stayed the same. This 2 is 2, this 2 is 2, this 3 is 3, this 2 is 2, this N is S. But these two things change. So these are called change points. So for given any suffix, its change points are the ones which will change in value when we take its LF. That means go to its previous suffix. So since this N changed to 2, 1, 2 changed to 4, that these are the change points. Okay. And this process of going step up here, like going up, is an LF mapping. So now we are seeing all of these suffixes, okay, as a part of this suffix tree. Okay. What are these numbers? So these numbers are the position numbers in the text. 5, 3, 6, 8, 2, 1, 4, 7, 9 are the position numbers in text. So these are the numbers. Okay. So for example, if I look at 4 and I look at 4 here, so what does this suffix 4 represent? So take its root to leaf path N, 1, 2, 3, 2, 2. So 4 is basically N, 1, 2, 3, 2, 2, right? So that is what 4 represents. So this is every root to leaf path represents a suffix, and this leaf maintains this number 4. That means this suffix is the one which starts at text position number 4. Now, what does LF mean in terms of suffix tree and in terms of the leaf of the suffix tree? What does LF mean? So for example, I know that T 3 through 9, that suffix, if I take LF, I get the suffix which is T 2 through 9. So this suffix I take this, right? But now where is 3 here? So 3 is 3 is here. right? Number 3 is in this circle, and number 2 is in this circle. Okay, so then LF mapping basically maps this leaf. It maps this leaf to this leaf. So when I write LF mapping, I write in terms of the leaf rank. So this is second leaf and this is fifth leaf. So LF of 2 is basically 5. That means LF of second leaf is fifth leaf. That's what it is. So basically, when we talk about LF, we are talking about leaf ordering. Okay. All right. So having seen this, let's think about what happens in the LF mapping. Okay. So let's say we talked about how these 3 changes, right? So we had this 3 and it had this thing n and 2, and we changed to 1 and 4. So let's look at 3. Where is it? It's here, n 2 2 3 2 2, right? So when it changed to 2, okay, its change points were, so this guy, this n changed to 1. So now when I come and put an extra, this n, instead of going here, it takes this bifurcation and it goes towards 1. Because this n changed to 1, it did not go here, right? N would be here, but n changed to 1. So instead of going this way, it goes on this branch. And then since these 2 change to 4, it will basically, instead of going this branch, it will basically go slightly here, but it basically is the same thing. It's basically the same thing. So this 2 goes to 4, but it's the same last branch, so it stays the same. So what happens is that at every change point, right, things shift rightward. So if 3 had these change points, at every change point, things shift rightwards, and that's where 2 is. Okay. So given 3, I want to identify where 2 is. So to calculate LF, and that basically I can say, okay, 3 is this kind of a path, but then this path will twist because every time there is a change point, it will move rightwards. Okay, and then every change point I can take into effect the effect of every change point, and then I find where this is. Okay, so roughly this is what could be done. So this is how it happens. Okay, there is a suffix, and these are the change points. And when I take LF, basically every change point branches to right, and then this basically goes somewhere else. Now the thing is, I know where this is, but based on this, if I want to find where this is, I have to somehow find out how much effect this change point has, how many positions forward it will put, how much effect this has, how many positions forward it will put. And if I have to count like that for every change point, there may be many change points in some suffix. It's going to be a costly operation. And it can be a costly operation at the query time. That's a bad part. So what we do is, how do we deal with this many change point situation? That's our main focus here. So our main focus is, how do we really deal with this many change point situation? Okay. So what I'm going to show you is, I'm going to show you this string. Okay. So this is 0, 8, 6, 9, 5, 1, 4, 3, 7, 1. This is a string. Okay. So if you look at here, it's the same thing, 0, 8, 6, 9, 5, 2, 3, 7, 1. Okay. So, and I'm drawing it, mapping it in 2 dimensions, so that values basically are along the y-axis. Okay. And then I'm actually pointing everything to its predecessor. So this is how it looks when this spread encoding looks when we look at things in 2 dimension. Now I put this extra character 2 in front, right? So I had this suffix. Now I put this extra. So I prepend something to the suffix. So you know that LF mapping is basically prepending to a suffix, prepending a previous character to a suffix. So when I prepend this 2, what happens is that I get something like this. So I prepend this 2 to this mix. So I get this 2 as a cutting line. That means all of these are above 2, all of these are below 2. So whichever arrows were crossing this line now will realign themselves to 2, because predecessor for all these 5, okay, will change and they will become 2. So all these 5 points are the change points. And how do we identify them? So these are all the points which are in the skyline of the area which is above this line. So take entire area above this line and look at its lower skyline. So these are the 5 points which form on there. So there are now 5 different change points. Okay, but a nice property about skyline is that if I know the last change point, I can figure out all the previous change points. If I know that this is the last change point, which is 3, I can figure out I don't have to look at anything else. I can figure out that 4 must be the before that, 5 must be before. Just looking at this without looking at what was the previous value. So that is a nice thing about Skyline, that all the change points can be characterized in terms of the last change point. So this is a key observation. All the change points can be characterized in terms of the last change point. So now what happens is that I still want to calculate LF, right? And here is the last change. Let's say this is I. This is I, and I want to calculate LF of I. And let's say there is a last change point somewhere here of I. Okay, there's a last change point somewhere here of I. And then I see, so let's say this is the last change point. Then I see, okay, there are change points here, 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 so on. However, what happens here is that, okay, I can characterize all these change point in terms of this, but they're still there. I cannot still, when I take LF, I still have to calculate which they are at query time, and I still have to find out. Okay, so instead what we do here is that instead of finding where LF goes, I'm going to write this I in terms of I prime, which is its LF successor. And then I'm going to say, okay, if both I and I prime have a last common change point right here, then all of their change points before are going to be the same. And that's why when I take LF, they are probably, this location is going to go in the same location. So what is LF successor? Okay, so I have this I, and I call I prime as its LF successor, so that when I take LF of I, okay, and let's say LF of I goes here, and when I take LF of I prime, and let's say it goes here, then they are next to each other, they are consecutive. So I prime, LF of I prime is basically LF of I plus 1. So that means that I prime is LF successor of I. Okay, so that is what it means. So now the good part is, since I'm talking about common things I and I prime, last common change point actually determines everything before. Okay, so now my goal is, if given I, can I find I prime, which is the LF successor of I? So that is my main idea here. Okay, so for that, what we do is that we write some information, augmenting information in every leaf, so that given I can identify I prime. So I write some information in I write similar information in I prime, and then I search, when I search from I go to I prime. So here we actually, to search from I prime from I, we actually put a few cases here. So first case is that, let's say I and I prime have this thing as their lowest common ancestor, that is LCA. Okay, and then above LCA, they have all these change points which are common, but suddenly this is a change point which is change point for I prime, but it's not for I. So what's going to happen? This is called first point of break. So when I take LF of I and I prime both, I keeps going on the same path, but I prime will suddenly bifurcate out of this path. And since I and I prime bifurcate right here, within this guy's subtree, I and I prime are going to be consecutive ones. So only one pair can happen like that. Okay, so as soon as I identify, so what I do is I write at I write where this FPB is, and as soon as I write this information, and I can do this in log sigma bits, as soon as I write this information, I can immediately find where I prime is, because it's the only one which has the same information as this guy. Okay, so this is case one in more details. So for example, here I know that LFS of 9, this guy's LF successor is this second one. Okay, so 9's LF successor is 3. What happens? What is this guy's LF? 8. What is 3's LF? 2, right? It's in one number less. So this, I'm talking about this guy and this guy. So 9 goes with LF to here, this goes to LF, and they're successors of each other, right? And that's why 3 is a successor of 9. Now what happens? Look at 3's and look at 9's change points. No change point at all. Look at 3's change point. 3 has actually a change point here at n. And that's why what happens is that 9 does not have a change point. 3 has a change point. So 3 bifurcates out of here, and then it goes on the right of 9. So 9, when 9 becomes 8, 3 becomes 2. Basically, at right this point, 2 bifurcated out and became a successor of 8. So this is what's happening here. Second case is that, let's say there is no breakpoint until LCA. So all of these change points are common between I and I prime. Okay, so then we can identify all these change points by using last change point. Okay, and then what happens is that I look at and I look at the last inversion that I can have, and then I look for I prime, which is immediately after this, which has the same information as I written. Okay, so I write these things, and basically it's the same information or written at both points, and I can find I as a I prime as something which has something qualified, something which qualifies, which comes on the immediately on the right. So if I look at here, right, I look at this 4 and 7, okay, and 4 goes to 3 and 7 goes to 6, so they are successors. So 4, so this guy's LF successor is this guy. But if I look in here, 4 has a change point at 1, but 7 and 7 has also a change point at 1. Okay, so 4 and 7 both have this change point. So this is their common change point. So if you look at this N1, 2, and then this is their LCA. Above the LCA, this is the last common change point, and it's the same. And everything after that is just nice and straight. So at this change point, it changes and goes into this part. Okay, and then it maintains the same order and stays this. So if I want to find this guy's LS successor, all I have to do is find the first qualifying node on the right of it, and that's where you find this one. Case 2b is something where everything is nice and same here, but then there is suddenly a change point right here. That means I prime, the LS successor of I, actually comes before I, and then this is called inverting case, because what happens is that because of this change point for I prime actually inverts over I and goes on the right side of I here. Okay, so in this case, we have a little more intricate solution, but if you want to look at in these terms, right? So look at this 5 and look at this 2, okay? So if I take this guy, 2, what is its LF? Its LF is 1, right? If I look at this 5, what is its LF? Its LF is 4. So these are successors, right? These are close to each other. So 2's LF successor is 5, but look at this. 2's LF successor is 5, and it's an inverting case because 5 is before 2. Now what's happening here? Look at 5. 5 has these change points, N and N. 2 has change point N. So 5 and 2 both have this change point, which is common. So this is the last common change point. But after that, 5 suddenly has a change point right after this bifurcation. And that's why this change point makes 5 go to right of 2. All right. So if I want to find this, what I do is from 2, I jump to the sibling node of this change point here. Then I find this change point. And then what I can prove is that within this change point, 5 can be the only one which has similar information as 2, and that's how I identify 5. There are several cases which are of proof, and when we want to find I, given I want to find I prime, there could be another pair J and J prime which may interfere. However, there are ways to avoid that interferences, and that's for more details, please read paper for that. Okay, so ultimately what we have shown is that from LF successor, we can do a repeated, we can compute LF. From LF, we can compute suffix array. From suffix array, we can do pattern matching. So finally, we have this result that we can do pattern matching in T plus OCC times polylog n query time. And the index, nice part is that index is now big O of n log sigma. So we basically broke that complexity barrier. And that's why we like this paper. Okay. So that's about it. And thank you for listening. I'm going to skip this more philosophical slide, and then thank you for listening again. If you have questions, please feel free to email me. Thank you.